So hello everyone. I guess you all are doing well, and I also guess that you all have gone through the previous two lectures of the SVM part of our series in ground0.ai. So let's have a quick recap before going into the hands-on session of making an SVM model using scikit-learn library in Python. Support vector machines, or SVM, is a supervised learning algorithm used for classification and regression. It works by finding an optimal hyperplane that best separates different classes. Hyperplane. A hyperplane is a decision boundary that separates different classes. In the image, we can clearly see there are two hyperplanes, one for first class, another for second class. Support vectors. Support vectors are the data points closest to the hyperplane that influence its position. Here we can see that these are the support vectors, and also you might have gone through the video where you have seen how these support vectors or these data points are selected by minimizing a certain loss function. Then margin. Margin is the distance between the hyperplane and the nearest data points, that is support vectors. Here we can see this is the margin. Then kernel trick. So kernel trick is the main reason why SVM is one of the most unique supervised learning algorithm. So kernel trick is a method to map data to higher dimension when it's not linearly separable, that is linearly inseparable datasets. Here I have taken a small example of the iris UCI dataset where I have taken sepal width and sepal length and used all the possible kernels that I know to map them. First is linear kernel, which you might have gone through in the first video. In linear kernel, so let's say we have three classes: white class, the blue class, and the green class. So in linear kernel, the white class is separated perfectly, the blue class is separated up to a certain extent with some of its part or remaining in the green class and some of green class parts remaining inside of it. And the green class is all separated pretty nicely with some of its part in blue class. The RBF kernel, also known as the Gaussian kernel, because of the function that it uses. Here also, the white part is separated very well. The blue part is although not separated well, but still we can see it's pretty decent. But we can see the domination is done by the green part where it has a major portion here. Then we have polynomial kernel. So in polynomial kernel, we can see it's the best out of all of these because the white class is separated perfectly. The blue part is actually separated well with some very few points outside of it, and also the green part is also separated very well, and you can see that some of the points pretty less compared to here is outside of it. In the sigmoid kernel, it's actually pretty less stocked off because of, you can clearly see is that it does its work very badly. And here you can see that the white part, the green part, the blue part all come under the white part, and the green part is here, and the blue part has very less of its portion. Now let's move to the coding part. So here we will be using Google Colab, and I also recommend you all to use Google Colab because all of the dependencies will run on cloud and there will be no pressure on your hardware or your system. So let's first go and install the dependencies, that is the libraries we will be using: NumPy, Pandas, Matplotlib, and scikit-learn. Generally in Google Cloud, you will see that all of these stuff are already pre-installed and you will have no problem on using them, or maybe you can go without doing this step. Then we have the imports. So for the imports, we will be importing NumPy. So NumPy will be imported basically for numerical operations. Then we will have Matplotlib basically for visualizing our dataset. So we will here, what we will do is that we will visualize our predictions after we train the model. Then we have the sklearn datasets, and from that we will be using load digits. So load digits is basically the popular MNIST dataset from that we used for as a big baby step into our deep learning journey, where we train a simple neural network to classify the handwritten digits. And then we have train test split imported from the model selection, basically to make train dataset split and test dataset split. Then we have SVC imported from SVM. So SVC, as you see here, is basically support vector classification in the sklearn.svm function. So I always recommend to go and check the official documentation and stuff, because you will actually get more knowledge of things here. So now let's see, we will also use metrics for getting the accuracy of our model, because that's a thing that we all make models getting a good accuracy on a dataset. Now let's load the dataset. So we will be using mnist dataset. So let's have mnist variable here, and we will be using load digits. And from here we will be actually using as frame. So we don't want it to be in a format of a frame. Here the classes is 10, so we want all the digits from 1 to 10 be present, and return xy false. It's not required actually. So here we'll set up go as false equal to false. We'll run it, and we will see that our model will be used. What an unexpected keyword error. So let's see what happens. Oh, sorry, it's actually as frame. And now let's split data into train and test. So we will take two variables x and y. So here we will have the mnist data part in the image form. So mnist data, and for the y part we will be actually using the target label. So mnist.target as type integer. Now we will be splitting the data set into training and test sets. So let's go for xtrain, xtest, ytrain, ytest. We will set up use train test split. It will actually show up when you click, and we will be giving our x part and y part that we defined above with our test size. So test size here is actually how much size of a data set you want to give for making a testing data set and a training data set. So generally it's 0.2. It's a golden number. So it's 80% of training and 20% of testing. And we will have a random state which basically shuffleizes or shuffles the data set into different parts. Now we are good to go with the dataset. Now let's train the model. So we will have SVM, and we will use SVC. Here we can see there are so many parameters in the official documentation of SVC, but we will be only using kernel, degree, and gamma. So and also C. So C is basically for class. Kernel is basically for the linear kernel, the RBF kernel, the polynomial kernel, and the gamma is basically a scale. So you can come here and read. So it's actually the kernel coefficient for the respective kernels. So here we will go with first kernel. We will be using linear kernel. I will suggest you to actually go and make different types or different kernels to test with. Here you can see linear kernel is there, polynomial is there, RBF is there, sigmoid is there, pre-computed is there. So now let's go for C. So C basically stands for number of classes. And then we have gamma. For now I'm taking gamma 0.1, but I will still suggest you to try with different values of gamma. Now we will go for svm.fit. So what svm.fit is that? So scikit-learn has this svm.fit or a model.fit feature where we actually fit the training data into the model, like our model gets trained. So we will go with xtrain and ytrain and make it so. Now we will see it happens, and every time we train a model, it will show which type of model we have trained and the respective parameters that we have given with the model. Now let's make predictions. So we will be making the predictions on the testing dataset, and here also scikit-learn provides a .predict function to predict on the test set. Now let's set our model for evaluation. We will be using accuracy metrics, so let's name it accuracy and metrics dot accuracy score. We will be passing the y test with y predictions that we have made. then we will be actually printing our result. And now we will see that our model has a pretty good accuracy of 97%. Here you can clearly see it has a high accuracy of 97%. Now let's write a function to visualize our data samples. So we will take def plot. Here we will pass index like number of we will run a for loop for it. Then we will write plot.im show x test index dot reshape. So here we will actually reshaping our images. So in load digits we actually see it's a 8 by 8 image. So here we will be passing 8, 8. And we will be having in gray, cmap equal to gray. Then we will like plot title. For that we will be actually showing key what was the actual one and what's the predicted one. So we will see predicted ypred and index, and then we will have the actual. Which will be actually y test index. Now we will have the axis off actually. And we will plot.show. Now let's run a for loop for I in range let's say 7. We'll just go plot I and we'll just simply run it. Sorry, access. And run it. Now we will see actually have 7 images with its predicted and actual. Here we can see actually we have predicted is 6 and actual is 6. I think from the image also it's clear. Here also predicted is 9, actual is 9, it's clear. Predicted is 3, actual is 3, predicted is 7, actual is 7, predicted is 2, actual is 2. So I think we have made our model and it works pretty well with a high accuracy of 97%. And I will suggest you to actually go and try with different kernels and play around with these cyber parameters. Not with the C1, but the parameters there actually, maybe the gamma function, maybe the tolerance, the KH size, and verbose, etc. max iterations. And I hope you liked it, and I also hope that you do well in the future. Thank you for watching the video.